Freya, how are you?
Okay,
Good
good
afternoon.
How was
afternoon,
class
everyone.
yesterday?
I'm going to meet all of us. So, good afternoon, everyone. You're welcome for our first lesson of chemistry. I'm going to request someone to lead us in a word of prayer. You can please raise your hand and you lead us in a word of prayer. Ruth, please put up your hand so I can make you a co-host so that you can help me in unmuting you.
And let me also lead in an opening prayer. And let's humble ourselves and we pray. Father Lord, we thank you so much for this chemistry lesson we are going to have. We ask that you may take control and help us understand whatever is going to be taught to us. We ask for a stable network and that everything we do that will be to the glory and honor of your name. Thank you for in Jesus' name we prayed. Amen.
Okay, thank you so much, Ruth, for leading us in that prayer. So, I prepared a lesson today that we will all study, and that is our first topic that we're supposed to cover in senior 4 second term. But before I go ahead to share with us in regards to that topic, may I know in the chat which topics we're able to cover this term at your different schools? I'm saying redox, oxidation, industrial processes. Okay, that is good. The periods of reaction, oxidation, fossils, effects of electricity on substances, chemical oxidation, industrial processes. Okay, that is interesting. So, we'll be looking at our first topic that we're supposed to look at next time, and that is periodicity, or what we call trends in the periodic table. So this is Shamathan. I'll be taking you through chemistry this week and next week. So, like I said, you're going to be looking at trends in the periodic table, or what we call periodicity. And of course, as we go about this topic, we'll appreciate a lot of things about the periodic table and why it exists the way it does. I know we looked at some of these concepts in senior 2 and in senior 3 when we're looking at more concepts. So I expect us to have at least an idea on some of the concepts we are going to discuss today. So, of course, we know that every topic we are covering, we need to know what learning outcomes, what do we expect to know by the end of that topic. And those are some of the things we always look out for if you're doing activities of integration. So it's important for you to know what are the learning outcomes I'm expecting in this topic. So may I have someone raise their hand so that they can read for us the learning outcomes?
Michael?
Definitely.
Excellent to you.
Trends in periodic table. Learning outcomes. But know the trends in the physical properties of the elements across the period in the periodic table. Part B. Know the trends in typical, physical, and chemical properties of, of simple of simple components of the elements on the third period. That's all. But the model that predicts physical end. So like what is incomplete? That's complete. Yeah. Part C. That's complete.
Okay, thank you so much, Michael. I didn't notice my microphone was muted. Thank you so much, Michael. Can we have someone read for us the keywords and the competence? Someone else? And those people whose mics are unmuted, can you please mute? Because it keeps saying a lot of feedback. Eh?
Nancy. Nancy, unmute. Okay.
Okay, the keywords are atomic number, atomic radius, configuration, group, metallic character, period, periodicity, periodic property, and trend.
Okay, thank you, Nancy. Can you read the competence as well?
Okay, competence. A learner should be able to appreciate the diversity of properties of elements and how these properties change across the periods and groups of the, I cannot say the other words.
Of the periodic table. Okay, thank you. And reduce the font. Okay, so in this topic, like I said, we'll be looking at the trends. And of course, those trends come along with the physical properties and chemical properties. But in this lesson, we'll major basically on the physical properties. And those physical properties, I know we've interacted with them on several occasions. Can I hear from some of us what physical properties we know? When we are looking at the periodic table, what are some of the physical properties we are expected to know? You can post your answers in the chat or you can raise your hand.
Handle.
Boiling points.
Okay, good. Thank you.
Teacher, also tensile string. The
Okay.
tensile string. Any other contribution, you raise your hand. The teachers asked for the trends in physical properties of elements across the periodic table. Baggins says density. Brian says the reactivity and the behavior of elements. Then Ricky says hardness. Alvan, boiling and melting point.
Okay, thank you so much, Ruth, and thank you to everyone that has contributed in your chat. Okay, so when we are looking at the physical properties, we are looking at those things that we can see, touch, observe, feel. What are some of those things that we interact with when we are going about the periodic table? But like I said, in this topic, we are basically going to look at the trends in period 3 and trends in group 1 elements. So it means as we go about the different physical properties, we'll look at them first in period 3, then we'll look at them in group 1. Of course, we'll look at the chemical properties of period 3 elements and then group 1 elements. And we need to understand that when we're looking at the periodic table, I'm sure different teachers told us that these elements are put in the groups where they are and periods because of the character that they show off. So you realize that if they're in group 1, that means there are those properties that bring them together. They have that thing that groups them together to belong to group 1. If they're in group 2, the same thing is happening. You find that they have those properties that bring them together to belong to period 3. So that is what we are going to look at in this lesson. And I request that at least you have somewhere to write, because I'm going to keep giving assignments here and there. And of course, I'll expect feedback after a few minutes. So I'll expect us to be jotting down somewhere. So if you don't have a pen or a book, please run very fast for it so that when we get to the assignment part, your hands on, not waiting for other people to tell you what they got. All right, so moving on, we have trends in physical properties of elements across the periods in the periodic table. So of course, we understand that when we are arranging elements in groups and periods, we arrange them according to their electronic configuration. Who can tell me what we use to write the electronic configuration? Is it the atomic number or atomic mass? What of those two terms do we use to write the electronic configuration of a given element?
In the chat, Martha Owen says atomic number as well as Chloe. And then it's atomic number all through the chat.
Okay, thank you. So when we are using atomic number to write the electronic configurations, that's what we come up with to know the arrangement of the electrons in the different energy levels. So we are going to study this table below, and of course, we are going to write the electronic configurations of these elements. There are just 3 elements. So we have lithium, which is 3. What do we expect the atomic number to be for lithium?
Adon?
What is the electronic configuration for lithium?
Pauline. Pauline, again, say your answer. Okay, let's hear from Magazine. Roslyn.
It's 3.
They asked for the electronic configuration. Jocelyn again.
It's 1 to 2. I mean 2 to 1.
Okay, thank you so much. So we have the electronic configuration for lithium as 2 to 1. So remember, when we're looking at the periodic table, we said that the innermost energy level can only carry a maximum of 2 electrons. So if this was our electronic structure, would have the nucleus having the protons and then the neutrons, and then we have our next energy level, which has 2 electrons as the maximum. And of course, we add another energy level as soon as that one is filled. So we'll have 2 to 3 because the innermost shell has 2 electrons and then the outermost shell has 1 electron, which gives us 2 to 1, which when you add the 2 plus the 1, it gives you the atomic number of lithium. So who can tell us the electronic configuration of sodium?
Maria.
It is 2 to 8 to 1.
2 to 8 to 1. Very good. Thank you. Then for potassium.
Brian.
It's 2 to 8 to 1.
2 to 8 for potassium.
From Kishan. Thanks, Kishan. Mary Shanice.
It's 2 to 8 to 8 to 1.
2 to 8 to 8 to 1. Okay, thank you. So when we are looking at the electronic configurations of these elements, you need to know what is the atomic number. And after knowing the atomic number, it helps you add up those things. Because I know most of us here, actually all of us, not most, all of us do math. So when you're stating the electronic configuration, it should align with the atomic number. So for example, if I add 2 to 8 to 1, it will give me 11, which is the atomic number of sodium. Then for potassium, 2 to 8 to 1, which is the atomic number of potassium. So looking at these, of course, we know these are elements in group 1. So in which period is lithium? By looking at the configuration, who can tell us what the period of lithium is?
Joshua.
Second period.
I don't think I
Period 2.
had that.
Joshua.
Period 2. Okay,
Yes.
thank you. This is period. Okay, and then in which period is sodium?
Ibra. Ibra. Okay, Linda.
Period 3.
Period 3, good. And then which period is potassium?
Linda said the answer.
Period 4.
Okay, thank you. Period 4. So you notice that the number of energy levels these elements have is the period to which they belong. When you look at lithium, it has 2 energy levels, which show 2 to 1. So that means its period is 2. Then sodium, the same thing, 3 energy levels. That means it's in period 3. Then potassium, So you see that as you go down group 1, the element moves to the next group. So it is that flow that we are going to look at and what causes them to occur the way they happen. So in that case, I'll ask to move to the next slide. I'm glad most of you understood these concepts when your teachers taught them. Okay, so we have the electronic configuration of elements in the same period. So those elements that we are going to look at are outlined down here. So you can post your answers in the chat and then some people can raise their hands to tell us what is the electronic configuration of lithium. This one we've already done, so I'll just write 2 to 1. Then what is the electronic configuration of beryllium?
Brian?
It's 2 to 2.
2 to 2, good. Boron?
Rosaline?
It's 2 to 3.
Wood? Carbon?
Esther? Sorry, team. The team unmute.
It's 2 to 4.
2 to 4, good. Oxygen?
Esther?
2 to 6.
2 to 6, good. Chlorine?
Kathy?
2 to 7.
2 to 7, good. Neon?
Kathy unmute.
2 to 8.
2 to 8, very good. So those are the electronic configurations of the elements in period 3. So who can tell us, sorry, in period 2, who can tell us what they notice about these elements? Please, those people writing on the screen, Rax, can you style up? Otherwise, I'll put you in the waiting room. Okay, so we have 2 to, what do you notice about the electronic configurations of these elements in period 2? What conclusion can you draw about them?
Ibra? And they failed to unmute. Yes,
I think they are unstable.
Then let's hear from Mary. Mary? Okay, Michael?
Okay, I think the electric configuration increases in the
They have 2 energy levels.
Ibra, we heard from you already. Michael, pardon again.
I think the electric configuration increases in the atomic number.
Okay, then lastly from the chat, Bella says they have 2 energy levels. Angel, they have 2 energy levels. Crimson says the electrons in the last energy levels keep on increasing. And lastly, they are in the same group.
Are they really in the same group?
That is what Annette says.
Okay, Annette, thank you for your contribution, but I don't think these elements are in the same group because you realize that the electrons in the outermost energy level are different. That means the number of electrons they have in their outermost energy level becomes their group. So when you look at lithium, it has 1 electron in its outermost shell. That means it's in group 1. Beryllium, 2 electrons, it's in group 2. Boron, group 3. carbon group 4 like that. So you look at the last digit on the configuration, that's the group of that element. So one thing I expected us to notice, which I saw coming up, is that all these elements have what? 2 energy levels. So you realize 2 to 1, 2 to 2, 2 to 3, up to 2 to 8. And then when you come to the outermost energy levels, they're increasing by 1, depending on how much you're moving to the right-hand side of that period. So from the left to the right of the period, there is an increment of electrons in the outermost energy level by 1. So at least those are the 2 I expected from us. Ibra, I don't know why your hand is up. Do you have a question?
Ibra, please unmute.
No, I don't have a question. Sorry.
All right, so we can move, I think, to the next slide. So of course, these tables, you can go ahead and fill them in your notes, because I don't want the things to be reflected on the next screen. That's why I keep rubbing them up. So we move to the next. There are a few questions here for us. So of course, we first looked at the group 1 elements. If someone was noting down or taking screenshots, you can relate on what we concluded on in group 1 elements. So what conclusion can you draw from elements in the same group? Because we looked at group 1 where we had lithium, we had sodium, and then we had potassium. So what conclusions do you draw? Because we say this is 2 to 1, this is 2 to 8 to 1, and then this is 2 to 8 to 8 to 1. So what conclusions do you draw from those elements?
Okay, let me first read from the chat. Louis says they have different periods. Baggin says they have similar behavior. Bree says they have the same number of electrons in the outermost energy level. Then someone whose initial is K says they have the same number of electrons in the last energy level. They have the same energy level. That is Ricky. Kishan says both have 1 as their last digit. Dr. Nakaungu says they have the same valency elements in the have, okay. 1 electron in the outermost shell, that is from Roslyn. Simon says they increase by 1, and then they have the same energy levels. People are mixing answers. But William says they are not stable. Let's hear from Tyra.
All the elements either lose or gain 1 electron to have
Tyra, pardon again.
all the elements in group 1 either lose or gain 1 electron to gain a stable electronic configuration.
Maybe before we move on, I need to correct that. They're either doing one of the things. They're either gaining or losing. So you can't tell us they are either losing or gaining. So please be specific. If you don't mind, unmute and recorrect your answer, please.
Tyra?
All the elements gain a stable electronic configuration.
So I didn't get you clearly, but I hope your response was they all lose 1 electron to gain a stable configuration. So they are, it's a one-way thing. They are not like group 4. So group 1 always lose that one electron to gain a stable configuration. So you should correct that, not they either gain or lose. It is losing, because for them to gain stability, they have to lose that one electron. If they gain one more electron, they will never gain stability. You keep adding electrons until they gain stability. Okay, let's hear from the next person.
Angel. Angel, unmute. Okay, Louis.
They have different periods.
And lastly, Esther.
They have the same number of electrons in the outermost energy level.
Yes. And Andrew as well in the chat says that there is gradual change in their properties. Okay. All right. To you, teacher.
Okay, thank you Ruth, for coordinating. Thank you everyone for your responses. People who are mentioning properties, I don't know where we've seen properties in what we just did in the tables up there, but I want to encourage us to always look at the question, analyze it, and relate it with what you're answering. So we have lithium, sodium, and potassium. So we look at their configurations, because in the table, that is what we did. We filled in their configurations. So one thing, if they say draw conclusions from what you observed up there, you need to look at what you did up there. And what we did was to write the configurations. And you notice that for all these elements, all the 3 elements, we have all of them giving us what? 1 electron in their outermost energy level. So that means they all have 1 electron in their outermost energy level. Or someone that talks about them losing that 1 electron to become electronically stable. That one is also suggesting that they all have 1 electron in the outermost energy level. And once they lose that 1 electron, they become stable. And then another thing you notice is as you go down the group, there is another energy level that is being added. Because remember here we had 2 energy levels. Here we have 3 energy levels. Here we have 4 energy levels. So that means as you go down the group, an extra energy level is being added, which causes them to belong to the different periods where they belong. So that is basically maybe what your conclusions would have. Okay, so we move on to the next. So that is the answer there, but of course you can construct it in a way you understand it, as long as at least you have the main points that you're explaining. Then we move on to part B. Part B, we had already tackled that one, so I'll just show us the answers that we were expected to have, but we don't repeat what we've already done. So we have elements in the same period have the same number of energy levels, like we saw for period 2 elements, we saw that they all had 2 energy levels. And then when you look at the number of electrons increasing by 1, remember when we looked at lithium, it had 2 to 1. When we moved to beryllium, it had 2 to 2. So that means the number of electrons is increasing by 1 in the outermost energy level until you get to what? To the last element in that period. Then of course we have an element here in period 3 and group 4 of the periodic table. And then we have some questions here to answer. So I expect us to give some responses. So element M is in period 3 of group 4 of the periodic table. What is the atomic number of element M? This
From the chat, Martin says 14. That's the
Yeah, well, that's your
atomic
thoughts
number.
in the chat. Or
Sorry for interruption. So Martin says 14, Bella 14, Esther 14, Benjamin 14, Crimson 14. Okay, 14 is the answer in the chat.
okay, thank you. Can someone tell us how they got that 14? Maybe someone can raise their hand and we request them to unmute and they tell us how they are getting the 14.
Pauline? Okay, Pauline's hand is down. Tyra? Ibra? Ibra, unmute. Okay.
I'm saying 14 because it is in group 4, period 3. In order to identify the group, we consider the outermost shell, which has 4 electrons, of which the 3 periods are coming from 2 to 8 to 4.
Okay, thank you, Ibra. That is good. Do we have any other hand?
No, but in the chat, Benjamin says that the number of energy levels is 3. Maximum number of electrons in an energy level is 8. So the electronic configuration is 2 to 8 to 4. And then Relay says that element M stands for magnesium, and its electronic configuration is 2 to 8 to 4. Then Claire, period 3. It's period 3, so it's 2 to 8. Then you have a dash there. Then you consider the group 4, so it's 2 to 8 to 4, meaning that it's 14.
Okay. Thank you all for your responses. So I disagree with someone who was saying M stands for magnesium. We know that the chemical symbol for magnesium is not just M, it's Mg. So that means we cannot say element M is magnesium. And for matter of facts, magnesium has an atomic number of 12, not 14. So I love the way people have described in the chat, and Ibra that explained to us. So we say period 3. If we say an element is in period 3, therefore we expect that it has 3 energy levels. So it has a digit there, then another digit there, and then another digit there. But we know that the innermost shell, the one closest to the nucleus, has 2 electrons. So of course we put those 2 electrons there. So we ask ourselves, what are the remaining 2 dashes going to have? Since it's a group 4 element, obviously that means the number of electrons in its outermost energy level are 4. So we put a 4 here. But of course, we can't move to the 3rd energy level if we don't have the 2nd. So that means the 2nd must have been filled already with 8 electrons. So that means you have 2 to 8 to 4. And of course, when you add 2 plus 8 plus 4, it gives you what? 14. Because this is 10 plus 4 giving you 14. So that means the atomic number of that element M is 14. Because it's in period 3, it has 3 energy levels, 2 to 8 to 4. And it's in group 4, that means it has 4 electrons in its outermost energy level. So I hope even those who had written in the chat that they didn't know what we had gotten are now together with us. Anyone who is still lost? Please respond in the chat so that we can know.
My brother Gemina says she's still lost. Okay, then another person is saying the element is potassium, that is piezo. Ricky is still lost. Ricky and Jemima are the ones who are still lost. Maybe they can unmute and ask because the rest are okay with it. Jemima, please unmute.
To get that thing, I'm still
Which half of the class is saying that you pardon once again on how to get the atomic number. Teacher, in the chat, oh, this one. My Brian would love to explain on the way he has understood what you explained. Brian, is it okay? Then teacher, your mic is also off. So we're not getting anything.
Oh, sorry. I think Brian can explain, then I can just build from there.
Brian, please unmute.
Well, thank you. According to me, they're asking us for the atomic number of M. And first of all, we have to look at the period and then the group. Remember that this element has 3 periods or 3 shells or energy levels. So the first energy level covers 2 electrons. The second energy level covers 8 electrons. So that is done. Then in the third energy level, since this element belongs to group 4, we expect it to have 4 electrons in the last energy level, which becomes 2 to 8 to 4. Now, when you sum up that number, that will be our atomic number. Since we said that the electronic configuration of an element is actually got from the atomic number of that particular element. I don't know whether someone is trying to get me or whether I'm right.
Yes, Brian, thank you so much. Okay, so I'll elaborate one more time. So please open your mind to understand. So when we have period 3, like Brian has said, we expect that that element M is not a symbol. M here, I don't want you to confuse it and say maybe it's a symbol of an element that you know in the periodic table. What should help you find what M actually is the period and the group where that element belongs. So I saw someone writing potassium, others sodium. I don't know how you got there. But the thing you need to understand, element M is standing for any element that belongs to period 3 of group 4 in the periodic table. And we said if an element belongs to group 4, and I've seen some people writing group 4 like this, please, this is very wrong. It's not chemistry. Group 4, groups are written in Roman numerals. That is why you see I have IV here. It's not for decoration. So it is something that you need to practice so that when you get to wherever you need to display this information, you display the right things. So when you're looking at group 4 elements carry 4 as the number of electrons in the outermost energy level. So I may ask, for example, if I am looking at carbon, who can tell me the atomic number of carbon? Let someone raise their hand, they unmute and tell us the atomic number of carbon.
Okay, Martha? Okay, Rodrigo? Yeah, failed to unmute, but the atomic number is 6.
6, very good. So if the atomic number is 6, that means when we are writing the configuration of carbon, it's going to be 2. Then because we've already removed 2 electrons, it will become 4. Then a quick question. What is the electronic number of silicon? Sorry, the atomic number. What is the atomic number of silicon in the periodic table?
If I've asked you to unmute, you first introduce yourself. You're calling yourself Home Lab. Please unmute. Okay, Michael Blair.
I don't know why I'm getting a lot of feedback. Ruth, can we just concentrate in the chat since people, I think, are posting answers there?
It's 14 from the chat.
Okay, so we have 14. So what is going to be its electronic configuration?
Michael? Okay, from the chat, Divine, Maria, Negesa, and the rest say 2 to 8 to 4, apart from there is Galaxy. Someone using Galaxy S8 says 2 to 8 to 6.
Okay, so when we are looking at 2 to 8 to 4, you realize that if we have 2 to 8, we have 2 to 8 here, and then 2, 4. Because when you add 2 plus 8, it gives you 4. Sorry, 2 plus 8, it gives you 10, then minus 14, which gives you that 10. So that means in that case, you're going to have 2 to 8 to 4. So like we said, when you're looking at the element M, which they have told us is in period 3. So what I wanted us to draw attention to is you realize that these 2 elements have 4 in their outermost energy level. So that means these elements will belong to group 4 because of the 4 in the outermost energy level. So that's the same thing we have here. When we have group 4, that means it has 4 electrons in its outermost energy level. If we say period 3, that means it has 3 energy levels. So in that case, like I said, immediately after the nucleus, we have an energy level. So for example, I have my nucleus here with protons and then the neutrons. My next energy level is going to contain 2 electrons, and that is energy level 1. So I'll put 2, 2. Then I'll move to the next energy level because that one is already full. So I have my second energy level. And because it belongs to period 3, that means it has the 3rd energy level. So in that case, that means this second energy level has 8 electrons on it already. So that means I'll have electrons there, 8 of them. So because I have 8 electrons there, that means it will be 2 to 8. But because it's in period 3 and it has a 3rd energy level, and it's in group 4 elements have 4 electrons, the outermost energy level. That means I have an electron there, I have an electron here, I have an electron there, I have another electron there, which makes it 2 to 8 to 4. And when you add these 2 plus 8 plus 4, it gives you 14 as the atomic number of that element. So if maybe further they had asked you to identify that element would be silicon. Because when you look at silicon, it has a configuration of 2 to 8 to 4. So that's where you understand that M is just used for relation to inquire if you know the knowledge about finding out the periods and groups of those different elements. So in that case, that means your atomic number would be 14. Your electronic configuration would be 2 to 8 to 4. If they had asked you to identify the element, that element would be silicon. Are we now together?
there anyone who has a question? If you have a question, you raise your hand. But as for the chat, the majority say yes. Joel, your hand is up. I think it was a mistake. Then Linda.
Excuse me, teacher. How do you find the
Yes.
electronic configuration of hydrogen? How do you write it?
Can someone respond to that question, please?
Let me respond. The electronic configuration of hydrogen, since it is in period 1 and group 1, it has one energy level and it has one valency electron. It has one electron. So the electronic configuration is just one. So that is it.
Okay, thank you, Ruth. Students, I want us to understand that you don't need to complicate this chemistry. Just understand that if I know the electronic configuration, if I know the atomic number of a given element, that means I can write its what? Its electronic configuration. So like Ruth said, when you look at hydrogen, hydrogen has one electron, or it's in group 1 and in period 1. That means it has one. So that means for it, even when you're writing its configuration, its configuration is simply 1. The same thing when you move to helium. Helium has 2 electrons. So its simple electronic configuration is just 2. Because it's in period 1, so it has only one energy level. And because it's in period 8, because remember we said when we have the outermost energy level being filled, that element qualifies to become a group 8 element. So when you look at helium, it has 2 electrons. That means its outermost energy level is completely filled, and that is why it belongs to group 8. So I just need you to go back and review your notes on periodic table, and then try out the electronic configurations of all those of the first 20 elements, because that is really where our scope goes. So find out each element of those first 20 elements. What is its electronic configuration? What is its atomic number? Yeah, and the easiest way you can do some of those things is by getting a song or a rhyme that brings them together. So that you're able to write them in order, and then you're able to get the electronic configuration. Okay, I know that people who are writing on the screen you're discovering, but can you please discover later and let us study in peace? So there is a mistake here. This is supposed to be 2 to 4, not 2 to 2. So this is 4, not 2, because of the 14 the other side. So we've already discussed that one. So now we move into the trends in the properties of simple compounds and elements of group 3. And we had discussed on this one the different properties that we expect. So I'll just throw them up here on the screen since we had already looked at them. So here we are going to have the different trends. So can someone identify for us the different elements in period 3 in their order, starting from the one in group 1 to group 8? So you tell us what elements we find in group 3 in their correct order.
Rosaline?
We have sodium, we have magnesium, we have aluminium, we have silicon, phosphorus, sulfur, chlorine, and argon.
Okay, thank you so much. That is good. So those are the elements we have in period 3. At least you should know them since they're the ones we are going to be looking at in our lesson today. So that is sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and then argon. Okay, so I will move on to the next. So what do you notice as you move from one element to another? I think we've over answered this question over and over again. So I'll just skip that and leave it for you to think, what did we discuss earlier on? So we have the different trends that are involved in the properties of period 3 elements. And those different trends, we have the atomic radius, we have the metallic character, we have the melting point, we have the boiling point, and we have the density. So these are the different trends we are going to look at. So this is where I want everyone to have a book and a pen, because there are different assignments attached to every one of these trends. So of course, I'll be giving us just a few minutes for us to work out, and then we are able to respond. So we are going to look at the first one, which is atomic radius and how it relates with period 3 elements. So we have trends in atomic radius. Before maybe we discuss what trends, what happens about atomic radius and a period, what is atomic radius? When someone tells you atomic radius, what quickly comes to your mind? Anyone to rescue us?
From the chart, Treasure says the atomic radius is the size of an atom. Tab B says that atomic radius is the radius of an atom. Then Ruben says that it's the radius of an atom. Kishan, that the radius of an atom. Benjamin says that it's the distance from the nucleus to the outer shell. And then someone who calls themselves Big Daddy. Please unmute, you first introduce yourself.
Atomic radius. Atomic radius is the distance between the nucleus of an atom and the outermost shell.
What's your name?
Daniel.
Daniel. And then lastly, from the chart, Joel says that it's the distance between the center of the atomic nucleus to the outermost energy level. Emmanuel, link between the energy levels. So that's it from the chart.
And then we counted something.
Teacher, over to you. Your mic is muted.
Sorry, so I was saying thank you all for your contributions. So when we are looking at atomic radius, the same way you hear radius and then atomic. So I know in our math we've interacted with circles, and we know that when we are drawing these atoms, we draw them in a circular kind of form in order to easily define them. So when we are getting the atomic radius, we are basically looking at that distance from the radius to the outermost energy level of that given atom. Or if you're looking at covalent bonds, I know most of us will interact with this knowledge when we offer chemistry at A level. But for now, we can give you the information that we can give for now. So when we are dealing with a covalent bond, remember in covalent bonding, there is sharing of electrons. So when we are sharing electrons, because I know we all remember that knowledge, we have the radius. We know that the radius runs from the center to the circumference. And then the same thing here. So if we have those two elements bonded together, that means we have this distance as d. So in order for us to get the atomic radius, we'll have d over 2. Because we need to know what is the distance from this point of one of from the nuclei of one of the elements to the nuclei of the second element. But if we are looking at one particular element, like we are going to do in period 3, that means from the center of that atom, where the nucleus is, to the outermost energy level of that element. That is what determines the atomic radius. So when you're looking at the radius, you're basically looking from the center to the outermost energy level. What is that distance between those 2 points? So that is what we are going to look at in accordance to period 3. So when we are looking at period 3, what is the trend of the atomic radius across that period? Because remember, in our previous slide, we've listed all the elements in period 3. So what do we expect the atomic radius to look like for all those different elements? So that is what we are going to really focus on here. So we have what is atomic radius? So we can say this is the measure of the size of a given atom of an element. But then to bring out the precise knowledge of what that atomic radius is, we call it the distance between the center of the nucleus of an atom and its outermost shell. And that is what I was trying to explain with that diagram that I drew. So we can move on. So you're going to study this structure here, and of course you're going to answer the questions that follow. So the structure is this one here. So who can identify for us the forces? What is force Y called when you look at this diagram? Force Y is here. What is force Y called according to the diagram?
Andrew calls it attraction. And then Brian, what do you have to say? Adam?
Forces of attraction.
Okay, that's what's coming in from both the chat and the hands.
Okay, thank you for your contribution.
Which are lastly from Treasure. Treasure says nuclear force of attraction.
Okay, thank you. So thank you for your contributions, all of you. So you realize that there is that bit of attraction. So that means those forces are called forces of attraction because we all know that in our nucleus, we have what we call the protons, which are positively charged, and the neutrons, which are not charged. Yet the electrons are negatively what? Negatively charged. So that means between this electron here and the nucleus, there is that attraction force because they are oppositely charged. So you find that there is that attraction. The protons are trying to attract. Like the same way you have in magnetism that unlike poles attract and like poles do what? Repel. So it's the same thing here. So why? Those are forces of attraction or attraction forces. And then when we go to M, what forces does M represent?
M for Treasure in the chat, she says those are repulsive forces. Queen Esther says forces of repulsion, and lastly from Blair. You fail to animate, but then Shapes says there's no force, and Daddy says there's repulsion. Then I think it's kind of requesting Big Daddy to change back to Daniel. Otherwise, won't be considered. Brian Okora says Van der Waals forces. Andrew, electron repulsion. And then, yes, repulsion.
Okay, so thank you. So we all know that I have just explained that when you look at a magnet, like poles repel. So it's the same thing here. You look at this force between electrons. And remember, these electrons, both of them are negatively charged. So that means they are going to repel each other. So when there is repulsion, those forces are called repulsion or repulsive forces. So was it Cherop who said no forces? I don't think that is true. So there is repulsion between those two. So that means it becomes repulsive force. Okay, so thank you for your contributions. So we will move on to the next. So that is what we have for those forces. So we have our next question. I hope maybe you took a screenshot or you can still remember this diagram here, because the next slide has some questions that we need to answer according to what we've mentioned on this slide. So I hope we can carry that knowledge into the next slide. So we have our question here. Which one of the forces above operates to decrease the size of the atom?
From the chat, Treasure says Y, Bella Y, Ricky says attraction. Someone who is called Home Lab says M, Ibra attraction, Divine attraction, Roslyn Y. Okay, Home Lab corrects himself saying that it's Y. Nakato Kathy says M. And the rest say Y. Nakato Kathy and Martha say M.
Okay, thank you so much, Ruth, and thank you all for your contributions. So when we look at the structure we had initially, if we are to go back to the other slide. When you look at this structure, remember, the more you attract something, that means the smaller or the more you reduce the distance between those two objects. So for example, if we have a magnet and our metallic substance, you realize that the more the magnet attracts this metallic substance, the more the space reduces. So attraction reduces the size of that what? Of that atom. So there is that reduction. As they attract, they reduce. As they attract, they reduce. And the reverse is true. As something repels, that means if something repels another thing, therefore it's going to be what? The distance between those two will what? Will grow bigger because there is that repulsion. They don't want to be next to each other. So because of that, not wanting to be next to each other, they repel each other, which creates a bigger size in the atom. But if there is attraction, that means the size does what? Reduces, like we are going to see in period 3, how those things happen. So here, when you look at this attraction force, because the nucleus is pulling this electron, you come, the distance will what? Will reduce. And that means the size of the atom also does what? Reduces. But the more this force M is imposed, the other electron says that, we look alike, why should you come? No. So it keeps doing what? Repelling it. So as it repels, that means the distance does what? Increases. And that increases the size of the what? Of the atom. Okay, so back to our slide. We say decrease in the size of an atom. We have why? Because of its attractive nature. And then increase in the size, of course, it remains M, and I've explained why. So here we come on variation in atomic radius for elements in the same period. We are going to study the structures. So remember we mentioned the elements in period 3. So I'm going to task you in your book, draw the different structures of the period 3 elements. We mentioned them, so I hope you noted them down somewhere. So draw their different structures, and then we are going to answer the questions below together after you have drawn. But for now, please just draw those diagrams, and then we can answer the questions thereafter together. So I am giving us, how many minutes should I give us? It shouldn't be more than 3. So I've started timing, it's 3:22. So that means at 3:25, we should be done with drawing those structures. Then Divine Care asking for pardon. I don't know what the pardon is about. Okay, Chips, thank you for that comment. So please, at 3:25, we are stopping. So Ruth, you will alert us. Home lab, we didn't ask for electronic configuration. I asked for the structures of those elements. That's why I've given us those 3 minutes to draw the structures, not the electronic configuration. Because when you draw the structure, we are going to be able to explain our questions as given to us. A Divine Care, I'm asking what your pardon is about, because I don't know what you want us to pardon you on. So I am not sure. Okay, that's good. Thank you.
It's time.
Okay, thank you, Ruth. So, have we all finished drawing the structures? Okay, at least I can see one done here. Someone is asking which drawings. I don't know what you want us to tell you about which drawings. Because I think the question is on the screen. If you have read the question, you would have. Okay, so I can see a lot of feedback of we are done. That is good. So our first question is right here. Identify the atoms with the largest atomic radius. So which atom has the largest atomic radius?
In the chat, Nancy says argon, Emmanuel argon, Mary argon, Ibra says sodium, Treasure says sodium, Tendo says calcium, and the rest say argon.
Okay, so anyone who can raise their hand and support their answer, you tell us your answer and you tell us why you think that answer is the largest atomic radius.
Michael?
Okay, I think it's argon. Argon is the atom with the largest atomic radius because it has the highest number of electrons in the outermost shell.
Let's hear from Queen Esther as well.
Okay, for me, I thought it was sodium because it has the least number of electrons, or it has the least number of protons in the period. Therefore, it has low attraction. Therefore, it has more repulsion. Therefore, it has the largest atomic radius.
Okay, thank you, Esther. And then, Lab, please use your actual name. Let's hear from Divine. Divine says
I think it's argon because it has the most number of electrons in its outermost energy level.
Thank you. Over to you, teacher.
Okay, thank you all. Chaps, you're saying you think it's calcium. Is calcium in period 3? Okay, so I just want to draw attention to something. Remember, on our previous slide, we explained something. And I want to interest us that if I had, let me try to draw the structures for sodium and for argon here. So for sodium, we say the configuration is 2 to 8 to 1. So if we have its structure, and so we have protons and neutrons here. Then we have 2 electrons here. And then 8 electrons in the next shell. And then we have 1 electron in the outermost energy level. This is sodium. And then we have our argon. Argon, which is 2 to 8 to 8. So we have its nucleus, which is protons, and then neutrons here. Then we have 2 electrons in the innermost energy level. Then we have 8 electrons in the next shell. Then we have the outermost energy level, which also has 8 electrons. So this one also has 2. Oh God. Okay, I have some notifications here that are not allowing me to do what I want to do. So I hope you bear with me. Those electrons are supposed to be in the right place here, but those notifications are giving me some hard time. So I hope we are able to synchronize. So here, when you look at these 2 structures, which one do you think its electrons are more closely attracted to the nucleus? When you look at these 2, argon and then sodium.
Martha?
I think sodium. Reason being on the outermost shell has only 1 electron. That means there's less force to to argon a large number of electrons, which makes it from the center. So I think it's sodium.
Andrew? Martha, please type your answer in the chat. You are breaking. Andrew, please unmute.
Yeah, thank you. I think it's sodium because the atomic size decreases from left to right in any periodic due to the effective nuclear charge to increase. Therefore, sodium has the largest atomic radius in period 3. Thank you.
Andrew, please re-echo your answer again.
I read again.
You say it again.
Okay. I've said, yeah, the atomic size decreases from left to right in any period due to the effective nuclear charge increase. Because sodium has the largest atomic radius in period 3 because of that reason. Thank you. Are we at par?
Thank you. Let's hand over to the teacher.
Okay, thank you so much, Ruth, for coordinating. Thank you, Andrew and Martha. So when we are looking at these electrons, I want us to understand, because as you go across the period, remember we listed the different elements in period 3. So we have sodium followed by magnesium. So they go on following each other. But remember, as we increase the what? As we go across the period, we are not increasing the number of energy levels, but the number of electrons is what? Is increasing. So sodium has only 1 electron in the outermost energy level. When we move to magnesium, it will have 2 electrons. When we move to aluminium, it will have 3 electrons, like that. So you find that there is an increase in the number of what? Of electrons. And if you can remember what we explained, that means the number of electrons that you're adding is increasing. That means the nuclear charge is also what? Increasing. To take you back slightly to the periodic table knowledge you studied in senior 2, when we are losing electrons, Remember for sodium, because of 1 electron in its outermost energy level, we said instead of gaining 7 electrons, which will require a lot of energy, we rather lose that 1 electron. So therefore, the nuclear charge for sodium, because of that 1 electron that it has, it will have a positive 1. Then when we go to magnesium, it will have a positive 2. So when you look at that trend, sorry. When you look at that trend, so sodium it's +1 for magnesium, +2 for aluminum, it's +3, and so on and so forth. So you realize that you're adding an electron. As you keep adding an electron, you're increasing the nuclear charge, like Andrew has said. Because the nuclear charge is increasing, that means the attraction, the nuclear attraction of those electrons is also what? Increasing. And because the nuclear charge is increasing, I want us to listen, and if I am slow, please you let me, if I am very fast, you let me know so that I can calm down a little. So when the nuclear charge is increasing, therefore the nuclear attraction is also increasing. And because the nuclear attraction is increasing, because remember we said as the electrons are attracted to the nucleus, that means the size goes on what? Decreasing. And because the size is decreasing, therefore the atomic radius also does what? Decreases. And that is why we say that atomic radius decreases from the left of the periodic table to the right of the periodic table. That is why we conclude that sodium has the largest atomic radius. And because of its nature, because remember, if this is our nucleus here, there is attraction. This one is a completely filled shell. This one is also a completely filled shell. That means this nucleus is holding them together. But this one with only 1 electron is almost being neglected because of the repulsion that it has. Because when you look at all these are 8 electrons, these ones here in this shell. There are 8 electrons. Even though they were to attract this 1 electron, the repulsive power is stronger than the attraction forces, onto the nucleus. But when you look at this argon here, argon, the attraction forces are almost similar and almost no repulsive forces. And that is why we say for it, it's a stable atom. So that means for it will have a very small atomic radius because of the attraction between the what? The elements. So when you look at sulfur, sulfur will also have a smaller atomic radius, looking at the attraction forces and the repulsion forces between the what? The electrons. So I know most of us will understand more of these details when we go to A level, but I just need you to understand that when we have the atomic charge increasing, that means the nuclear charge increasing, that means the nuclear attraction also does what? Increases, which decreases the atomic radius. So you need to understand that as you go from sodium to argon, the atomic radius is decreasing. And it's decreasing, that means the size is decreasing because of the increase in nuclear charge, which increases the effective nuclear attraction of those electrons to the nucleus. So of course, I wrote down some of those notes down here, so we'll keep following through as we read, but I thought we should explain them before we move to that point. So I don't know if people still have some questions, but of course, some of those questions we'll answer them as we go about the slides, because I wrote some of those things down there. So I hope we've removed the query of saying between sodium and argon, which one has the largest atomic radius.
And I thought Mercy is saying that, teacher, you mentioned something about nuclear charge. Please elaborate more about it.
So I said when you're looking at nuclear charge, for example, I gave an example if you are following. I said we have sodium. And we know the electronic configuration of sodium is 8 to 1. And then we have magnesium. What is the next element there after magnesium?
Aluminium.
And then the next?
The electron.
Silicon. So I can stop here for now. 2 to 8 to 4. Remember, I said when you're looking at these elements and you're drawing their structures, this one has 1 electron in outermost energy level. That means its nuclear charge is +1 because there is an electron in its outermost energy level. When you move to magnesium, you add 2 electrons to the outermost energy level to give you that 2 electrons here. So that is 2 to 8. So this becomes its nuclear charge. When you go to aluminium, there are 3 electrons that put in the outermost energy level. So it gives you a +3, which becomes its nuclear charge. When you go to silicon, it has 4 electrons. So that means you added 4 electrons in the outermost energy level. Because on filling the second energy level, you need 4 electrons in the outermost energy level because silicon belongs to group 4. So that becomes the nuclear charge. So the number of electrons contained in the outermost energy level basically gives you the nuclear charge of that element. So that means as you go about the So as you go about filling those different So as you go about filling those different energy levels, you realize that the nuclear charge is increasing because when you look at this one, when you add the configuration, this is giving you 2, that is 11. So that means there are 11 electrons in that whole shell of sodium. When you come to magnesium, it's giving you 12. So that means you have +12. Those are 12 electrons in the outermost energy, in the whole shell of magnesium. Then when you come to aluminium, there are 13 electrons. That means when you look at the whole structure of aluminium, it has 13 electrons. So when you look at these figures, you realize that there is an increase in what? In nuclear charge. And because there is that increase in nuclear charge, it is going to automatically give you what? An increase in the attraction of those electrons. And once there is an attraction, we've said, once the attraction increases, that means the size decreases, which gives you a smaller atomic radius as you go across that given period. So it is basically about how many electrons are you adding to the outermost energy level. And then, of course, the more you add, the more it increases the nuclear charge of that particular element. So the more electrons you add to the outermost energy level, the higher the nuclear charge also what? Increases. Because remember, if I add an electron, that means the element changes to become another electron. If I add another electron, still the same thing is going to what? To happen. So if I come here, there will be 14. If I go to the next one, which is phosphorus, it will be +15 because I've added an electron to become 2 to 8 to 5. And when I go to chlorine, it will become, sulfur first. So if I go to sulfur, it will become +16 because I've added an electron, which becomes 2 to 8 to 6. Then if I go to chlorine, it will become +17, which means I have added an electron. I go on adding an electron. So that means the nuclear charge in that context is what? Is changing and increasing at that point per +1 for each element that I am moving to. I don't know if I am making sense by what I've just said.
The teacher, for the non-metals, the ones that gain the nuclear charge. For this reason, we just add, would not, I don't know how I can ask it, but as for sodium, magnesium, aluminum, yes, aluminum.
Remember, I
Where
am
does
just
that?
adding. Remember, I am just adding an electron. So that means I am considering the nuclear charge to be the number of electrons I have at that particular time. That is why
In
I
the
have
whole
continuous.
atom.
Yes, in the whole atom, not particularly the one I am
The
adding
outer
per
one.
time. Yes.
Oh, okay.
Okay, so
Pendo.
So, teacher, what about the non-metals? I'm a little confused about it. Is it the same thing? You just follow the number of electrons?
yes, I think that's what I've just answered, that you follow the number of electrons in the whole shell, not only the ones in the outermost energy level.
Meaning the number of electrons in the whole atom is the nuclear charge.
Yes, it's what is giving you the nuclear
Oh.
charge of what is that particular atom is carrying.
Okay, so someone is, I think they have also been answered because earlier on they were asking, is nuclear charge related to oxidation number, but they have been answered as well.
Okay, so we move on to the next slide. So this slide was supposed to come before atomic radius, where we have the periodic trends and of course both physical and chemical properties vary depending on what kind of pattern we have, and that is what we call the periodic trends or periodicity, because of the variations in the physical and chemical properties of group 1 and period 3 elements. And that cuts across for all the others, but since our major focus in this topic is on period 3 and group 1, that is where our periodicity knowledge will really centralize. So like we've been explaining, so we have give reasons. Sodium has the largest atomic radius because it has the least nuclear charge. And of course, we've seen it has a +1, and the outermost electrons +11, and the outermost electrons experience least nuclear attraction. That is what I explained, that one electron experiences the least kind of what? Of attraction, which results into the greatest distance. Because remember, we said when there is repulsion, that means the distance does what? Increases. And that means if it has increased between the nucleus and the outermost energy level, because remember, when you look at sodium, it has a configuration of 2 to 8 to 1. And I said, when the nucleus attracts this one with 8 electrons, is shielding the nucleus from attracting this one, because for it has a lot of energy to shield the nucleus from attracting this one electron. So it means because this one electron is repelled by the nucleus, it increases the distance between the nucleus and the outermost energy level, which increases the what? The distance. And because that distance increases, that means the size of the atom also does what? Increases. And because the size of the atom is increasing, therefore sodium comes up with a larger atomic radius in period 3. Then for the next, we know that argon has the smallest atomic radius because of the electrons that have the greatest nuclear attraction. So if these elements are all attracted to the nucleus because of its even stability, so that means there is a small distance between the nucleus and the outermost energy level, hence giving you what? it's giving you a smaller atomic radius for argon. So I think we've explained that. This is just information to help you understand it better. So you can either take a screenshot or I think Mr. Kaziwa posts these videos on the YouTube. You can go back and see more and watch more and also see more on what these things are about. So for periodicity, we've said those are the variations in the physical and chemical properties of the different elements according to their groups and periods. So it is basically about the variations in the trends. That is what periodicity is about. And that is why we gave you the factors, which is atomic radius, metallic character, boiling point, melting point, and then density. How do they differ? How do they vary from group to period? From period to the different elements in that period or the different elements in that group. So I think if there are no more questions, they're asking us to state the trend in the atomic radius of period 3 elements. So what is the trend of the elements in period 3? Who can tell us what I think? What is the trend of the elements in period 3?
In the
Okay.
chat,
Yes, Ru.
in the chat, Ibra says it increases from left to right.
Again increases. I think after the huge explanation, we should now understand what happens there.
The atomic radius decreases from left to right across the period.
Okay, I couldn't say better. That is the final conclusion that we draw. So anyone who had any suggestions, please conform to that. I think he can repeat it.
The atomic radius decreases from left to right across the period.
Okay, thank you so much. So that is what we understand by those different concepts. So atomic radius across the period decreases from left to right. So that is very important. Even when you're saying it reduces, you must be specific. If I was the one marking you, I would circle what does it mean. So that means it decreases the atomic radii of period 3 elements decreases from left to right, or the atomic radii decreases from left to right across period 3. So someone is saying, I haven't understood how it moves from left to right. When you're writing a periodic table, the periodic table has the left side and the right side. So the left side is what we call the one that usually has the metals, which is sodium and magnesium in this case for period 3. And then as you keep moving to the left, as you keep moving to the right, you find the non-metals. So basically, when we say from left to right, you're looking at the side of the periodic table. If you have the periodic table placed in front of you, you have the right hand and the left hand. So it's decreasing from the left to the right across that period. So that is it all for today. So please, if you haven't understood, go back and watch this video. And also ask the Holy Spirit to teach you. He's the best teacher. He will understand this chemistry, because I feel chemistry is one of the simplest sciences. But that's if you choose to understand. If you choose not to understand, it will be hard. So open your spirit to always understand. Every time you're coming for a chemistry lesson, allow yourself understand. If you've not understood, ask questions. If you haven't understood still, go back and watch the video. It will actually do you a lot of good. So ask the Holy Spirit to teach you every time you're coming for any lesson. You will clearly understand most of those things. So in our next lesson, we'll be looking at metallic character and then the remaining properties. So I expect us to go read about them so that when we come, we have an informed view and we share together. So that is all we had for today. So do some research, and thank you all for attending the lesson today, and thank you for being an active class. I always love teaching active students. They keep you awake and alert. So thank you all, and thank you so much, Ruth, for coordinating. I think that is all from me today. Have a lovely evening and God bless you. But before we close, can someone lead us in a word of prayer?
Just sorry for the interruption. Please help there are some people asking for the WhatsApp group link. Some are asking for the senior 4 WhatsApp group link as well as the one for senior 3. So you may help post it in the chat.
Let me see if I can first it. If I'm able to, then I'll share it. You can stay on for some minutes. But meanwhile, as I get the link, can someone pray for us?
Let's have ourselves for a word of prayer. Mighty King of glory, Abba Father, we thank you for this day. We thank you for this lesson. We thank you for our teacher. Thank you for blessing her with knowledge. I pray that as we are going to go to our respective places, may you guide us, O Lord. Father, Lord, help us to understand better as we read. Give us the strength to always read harder and read smart. We worship you. There is none like you. In Jesus' name we do pray and believe. Amen.
Amen. Thank you so much. So let me just get the link here and share it with us in the chat. But now, why is us